Hello, everyone, and welcome back. For today's topic, we're going to be solving exponential equations. And so there's a few different types that we're going to be looking to solve, but the first type will be in the case that we can rewrite these with the same base. So notice here that we can rewrite 81 as being equal to 3 to the power 4, and 27 we can write as 3 to the power of 3. For this topic, it is worth trying to kind of cycle through. Remember your powers of 2, 3, 4, 5, and 6, because those are kind of the most common ones we're going to be looking at. And if you can quickly identify these particular facts, you'll find this much easier to solve. So, at any rate, let us replace this 81 with 3 to the power 4 and this 27 with 3 to the power of 3. And so, what we end up with will be 3 to the power of 4 to the power of 4x is equal to 3 to the power of 3 to the power of 3x minus 2. So here we have the same base, but before we go ahead and simplify this, I would like to clean this up a bit first just to show what this looks like. Okay, so on the left side, 4 to the power of 4x means we've multiplied the exponents. So this will be 3 to the power of 16x. And on the right side, it'll be 3 to the power of 3. Now remember, you multiply the exponents here, so it'll be 3 bracket this 3x minus 2. And so now that we have the same base, we can drop the base and work directly with the exponents. So now we're interested in solving 16x is equal to 3 times 3x minus 2. And so here, let's expand out this 3 onto both terms. And so what we end up with will be 16x is equal to 9x subtract 6. Subtract 9x from both sides. So 7x will be equal to negative 6. Divide both sides by 7. And this will give you x is equal to negative 6 over 7. And so what it means in this particular instance to solve this equation is the point of intersection between these two particular equations. Okay? So for example, if this started off as 81 to the power of 4x minus 27 to the power of 3x minus 2, for exponentials, it's fairly common to set one side equal to the other and reduce down the bases in order to solve. So in this next example, we have the fifth root of 16 to the power of x is equal to 8. Now, it's worth noting that you can write have a fractional exponent. So suppose you have something like, say, a to the power of m on n. That's equal to the nth root of a to the m. So that's the case we have right now. Or what we can do is write this as the nth root of a all to the power of n. So note that all versions of this are equivalent. N is what we call the index. And it asks the question, what number times itself n times produces a? So primarily we've had a lot of focus with square roots, but there's nothing special about the square roots. We can still sum them with all of the other indices. Okay, so we have 5, the fifth root of 16 to the power of x is equal to 8. So we're going to rewrite both with a base 2 because 16 is the same thing as 2 to the power of 4. 8 is the same thing as 2 to the power of 3. So we will rewrite both sides with base 2. Okay, so, but first we're going to put it into the form a to the power of m over n. So the 16 will become 16 to the power of x over 5 is equal to 8. 16 we just said was 2 to the power of 4 to the power of x over 5 is equal to 8, which is going to be 2 to the power of 3. And we'll combine these exponents now. So keep in mind that this is going to be 4 over top of 1. So you can just multiply the exponents directly. So 4 times x is 4x, 1 times 5 is 5. And so this will be 2 to the power of 4x over 5 is equal to 2 to the power of 3. Now we may work directly with the exponents. So here we've got 4x over 5 is equal to 3. Multiply both sides by 5 yields 4x is equal to 15 because 3 times 5 is 15. Dividing both sides by 4 yields the fact that x is equal to 15 over 4. Okay, and so all we did was rewrite our indice in terms of instead of having the square root radical, we just instead made it a to the power of some fraction. And we could still rewrite these with the same base and solve it the normal way. I haven't covered a negative exponent yet, and so thought it might be time. So recall that if you have something like a to the power of negative m, that's equal to 1 over a to the m. And if you run into a over b to the negative m, that's equal to b to the m over a to the m. So here we're going to simplify the following as a single power. And we've got some sort of barbaric cubed root of 25 times 1 over 125 times 625 to the power of 10. So all of these can be rewritten as a power of 5. So let's see how this is done. So recall, again, we don't like the cubed root of 25. So we will rewrite this as 25 to the power of 1/3. Here we have 1 over 125, and we prefer to have this not as a negative exponent. So we can rewrite this as 125 to the power of negative 1, kind of via our formula here. And 625, we can leave that as is for now. Okay, so let's rewrite these all as a power base of 5. So 25 is the same thing as 5 squared to the power of 1/3. 125 is the same thing as 5 to the power of 2. Sorry, 5 to the power of 3, well, to the power of negative 1. And 625 is the same thing as 5 to the power of 4, to the power of 10. Let's go ahead and clean up all of our exponents here. So 2 times 1/3 is the same thing as 5 and 2/3. 5 to the power of 3 to the power of negative 1 is the same thing as 5 to the power of negative 3. And so we've established the relationship between the fraction and the power. And 5 to the power of 4 to the power of 10. So 4 times 10 is going to be 40. And now let's combine these at high speeds. So since these are all the same base, we can just add the exponents. So this will be 2/3 plus negative 3 plus 40. Okay, so negative 3 plus 40 is going to be 37. So this will be 5 to the power of 37 and 2/3. We never have mixed numbers. This is just a convenient way to simplify it. So turning this into an improper fraction, we go 37 times 3, which is going to be 111, plus 2. So this will be 5 to the power of 113 over 3. And there is our simplified power. And now we're interested in solving the following. So we now have here 7 to the power of x minus 4 plus 3 times 7 to the power of negative x. Now note, we should have a caution here. You cannot take 3 and times it by 7. So notice here that the bases are not the same and that 3 has an exponent of just 1. So we cannot combine these things together. So what do we do? Well, we've had a look at this question a number of weeks ago, but it had slightly different structure. And so here, our main concern is that we seem to have the 7 to the power of x and the 7 to the power of negative x term. So a reasonable first step might be to eliminate this 7 to the power of negative x. And we already have another positive 7 to the power of x, so we can multiply both sides by 7 to the power of x. So what happens when we do this? Well, we're going to expand this out. So here we have 7 to the power of x times 7 to the power of x minus 4 times 7 to the power of x plus, now it's going to be 3 times 7 to the power of negative x times 7 to the power of x is equal to 0. And I admit, this looks much worse than what we had before, but maybe perhaps let's clean this up a bit. Okay, so 7 to the power of x times 7 to the power of x, the base is the same, so we add the exponents. So x plus x is 2x minus 4 times 7 to the power of x plus, now here, 7 to the negative x times 7 to the power of positive x, keep the base, negative x plus x is 0. So this will be just plus 3. And if you've noticed, this should look familiar from before. So recall that we did have a look at this where we had the circumstance, and perhaps I'll write it a little bit more clearly. We can rewrite the 7 to the power of 2x as 7 to the power of x squared. And we also could have got that because 7 to the power of x times 7 to the power of x is something times itself. An example of this is 7 times 7 would be 49, or it would be 7 squared, which is what we're going for here. And so we can do a u substitution. We will let u be equal to 7 to the power of x. And so noticing here that 7 to the power of 2x is equal to 7 to the x all squared. This will become u squared minus 4u plus 3 is equal to 0. We play the most dangerous game. What numbers multiply to make 3 but add to make negative 4? So those numbers will be negative 1 and negative 3. And so now that we entered uland, we've completed our journey. We can now leave uland. And so when we replace the u's by the 7 to the power of x. And so what this really will become is 7 to the power of x minus 1 times 7 to the power of x minus 3 is equal to 0. Now notice we could have gone from this step directly to this step. It's just that it's a little tougher to kind of see this the algebraic substitution, especially in the case that if this happened to be like a cubic or a quartic, might be more difficult in case we need to use synthetic division. So it's quite okay to make a substitution of this kind. Okay, so now we need to solve the two leftover equations. And previously before, we actually just stopped by factoring this. Now let's go ahead and solve it. So here we have 7 to the power of x minus 1 must be equal to 0, and 7 to the power of x minus 3 must be equal to 0. So plus 3 on both sides gives us 7 to the power of x is equal to 3. And we can solve this by using the exponential equivalent and writing this as log base 7 of 3 is equal to x. And that's one of our solutions. And so here we have the question 7 to the power of x minus 1 is equal to 0. You could go proceed down the exact same path from before, but if you notice, this is saying 7 to the power of something subtract 1 is equal to 0. And recall that if you have something like, say, a to the power of 0, that's equal to 1. So here, by inspection, I can see that x is equal to 0 will be one of our solutions because 7 to the power of 0 is 1, and 1 minus 1 gives us 0. Here, solving this one, log base 7 of 3 is equal to x, yields x being equal to 0.56 after applying the change of base formula. Okay, let's try out another example. So one of our last examples here, we're interested in solving the following. 3 to the power of 4x minus 1 is equal to 5 to the power of 2x plus 1. And part of the problem we're going to have with this one is that we cannot write this in terms of the same base. Well, and if we try to, we're gonna run into different problems. And so here we need a new method to solve this one. And so we will make use of two pieces of data or two reference points from the past just in case. So the first way to solve these things is actually to rewrite these both with instead of exponentiating each side, we're going to take the logarithm of both sides. And we'll use base 10 because the base doesn't matter. And so we will write this as log of 3 to the power of 4x minus 1 is equal to log of 5 to the power of 2x plus 1. Now we make use of this fact. Suppose we have log of x to the power of n. That's the same thing as n times the log of x. So this n can be brought down. So in this case, if n was equal to 4x minus 1, we could bring this n down and replace it by the 4x minus 1. It's just we need to put the bracket around here. And so we can rewrite this as, in bracket, 4x minus 1 multiplied by the log of 3 will be equal to this 2x plus 1 times the log of 5. And so now we need to go ahead and do our distribution. So normally we do left-hand distributions. This time we're going to take the log and multiply it onto both terms on the inside. Note that log 3 and log 5 are both regular numbers, meaning they're just some sort of decimal, but we're not going to break this down. We're going to keep an exact value. Okay, so 4x times log of 3 will be the first term, and log 3 times negative 1 will be negative log 3. So notice here, we're taking the part in brackets and we're multiplied into what's in front of both of the logarithmic terms. Okay, so here's the 4x, here is the negative 1. Okay, similarly, on the right side, 2x times log 5 will be 2x log 5. 1 times log 5 will just be plus log 5. So why did I do this? This doesn't seem to have really helped too much. I do promise it will. So note, I want you to keep in mind about fundamentally, this does look very complicated, but essentially this is x times some terrible decimal minus another terrible decimal equals 2x times log 5, which is a terrible decimal, plus log 5, which is another not so great decimal. So what we're going to do is collect all of our x terms on one side and collect all of our regular log terms on the other. So that is minus 2x from, so let's move the 2x log 5 to this side and move negative log 3 to the other side. So doing this will yield 4x log 3 minus sign 2x log 5 is equal to log of 3, because negative log 3 we added, plus log of 5. Now we make use of this information. So both of these contain an x, and essentially this is a glorified version of this. Ax minus bx is the same thing as x times a minus b. So we can factor out an x from both terms here. So factoring out an x left over, we will have a 4 log 3 minus 2 log 5 is equal to log 3 plus log 5. And now we want to get the x term by itself. So how do we do that? Well, keep in mind this 4 log 3 minus 2 log 5 is essentially just one number, albeit not so pleasant number, but one number nonetheless. So it's like some decimal minus another decimal. So we're going to divide both sides by 4 log 3 minus 2 log 5. So what does that give us? Well, x, which will be equal to what? In the numerator, we're going to have this log of 3 plus log of 5. And then in the denominator, we're going to have this 4 log of 3 minus 2 log of 5. So this is the exact answer for what it is. And so if you would like, you can go ahead and type this into your calculator. 2.30359 something something something. So I'm going to call that 2.30 after rounding. And so this solution, if insert into the original, will balance that particular equation. So let's try one more of these. So in this last example, we're going to be trying to solve 5 to the power of 3x minus 4 is equal to 2 to the power of x plus 3. We're going to mimic the exact same steps that we did in the previous question. And I do encourage you to pause the video and try this one out for yourself. Take a couple of minutes and see how you did. Okay, let's get started. First thing we want to do, take the log of both sides. So this will be log of 5 to the power of 3x minus 4 is equal to log of 2 to the power of x plus 3. Bring down the exponent in both cases in brackets. Note, the biggest mistake I see students make here is that they don't put this part in brackets and they end up having 3x minus 4 times log 5. But remember, it's the whole thing has to be in brackets. This will be equal to x plus 3 times the log of 2. And so now we need to do a right-hand distribution. So this log 5 goes multiplied onto both terms. The log 2 gets multiplied onto both terms. And so 3x times log 5 will be 3x log 5. Note that when you're multiplying these things out, you don't apply the argument, this 3x, onto the 5. Okay, that's something done with the quotient and product law of logarithms. All right, negative 4 times log 5, x times log 2, which is x log 2, plus sign 3 log of 2. So there's not really a nice way to simplify these down. So you might be wondering, hey, can I just bring the 3 up here and make this log of 2 to the power of 3, which is log of 8? Absolutely. There's nothing wrong with that, but just for these ones, like you can't actually simplify these down enough to the point where it's a nice solution. And so for our purposes, we just leave it as is. Okay, so we move the x log 2 over to the left side, the negative 4 log 5 over to the other. And so we will have 3x times log 5 minus sign x log of 2 will be equal to 4 log of 5 plus 3 log of 2. At this point, we notice that both these two terms contain an x log here, like contain an x, so we can factor them out of both. And so we'll end up with x outside of 3 log 5 minus log 2 is equal to the right side. This 4 log 5 plus 3 log 2. We divide both sides by 3 log 5 minus log 2, and this will yield x is equal to 4 log 5 plus 3 log 2 all over 3 log 5 minus log 2. And from here, that's close enough. Again, we could simplify just the numerator and then simplify just the denominator, but we'd still have a log over a log, which doesn't noticeably decrease the difficulty yet. And so at this point, go ahead and type this into the calculator to confirm you get the same thing I do. Because again, this is my exact answer, but the calculator answer, because sometimes the question wants that, will be, now as an exact answer or an exact decimal answer, and when I say exact, it's because I'm going to include ellipses at the end, 2.05969. And if I took forever, I would write out the rest of the decimals. But for our purposes, we'll round this just to 2 decimal places. So this is about 2.06. Okay, so the homework questions have plenty of examples of each of these types that we're going to solve. And tomorrow we're going to look at solving logarithm equations. But for now, I think that's a good place to stop.